What if I told you that every single morning you're throwing away something that can generate real electricity? Not a joke, not a trick, not some science fair gimmick. I'm talking about something sitting in your kitchen right now, something you made yourself, something you were about to dump down the drain. And once you see what it actually is and what it can actually do, you are never going to look at your kitchen the same way again. Stay with me, because what I am about to show you took me 11 months to figure out, and I'm going to give it to you in the next few minutes. This is Simple Secrets Daily, and we dig up the knowledge that the modern world forgot. Before we get into it, if you're new here, hit that subscribe button right now and tap the bell. I release videos just like this one regularly, practical, real, science-backed discoveries that most people have never heard of. And if this video changes the way you think about your kitchen, drop a comment below and tell me. That means everything to this channel. Now let us get into it, because this one genuinely floored me. For 11 months, I did the same thing every single morning without thinking about it. I made my coffee, I dumped the grounds, I squeezed my citrus, I tossed the peels, I boiled my potatoes, I poured the water down the sink. Every single day, same routine, same waste. And I had no idea, zero idea, that I was throwing away one of the most important chemical components in all of modern technology. I was throwing away electrolytes. And not in some vague nutritional sense. I mean actual functional ion-carrying electrolytes. The exact same chemical component that makes every single battery on Earth work. Every phone battery, every car battery, every AA battery in your drawer. They all depend on electrolytes to function. And I was pouring mine down the drain every morning before I even finished my first cup of coffee. The morning I figured this out, I just sat at my kitchen table for a long time, staring at the coffee filter in my hand. Because it changed everything about how I saw that room. And that is what this video is about. Not just the experiment, not just the numbers, but the shift in how you see ordinary things once you understand the chemistry happening inside them. Let me tell you exactly how I got here, because the path matters. About 6 months ago, I was running low on copper sulfate solution. I use it for electrochemistry experiments, and I had completely run out of my stock. Rather than wait for a new order to arrive, I sat down and made a list, a very simple list. Everything in my kitchen that I knew contained dissolved ionic compounds. Natural acids, mineral salts, organic electrolytes. Just going through my cabinets and my fridge and writing it all down. And the list ended up being much longer than I expected. Coffee came first. Most people think of coffee as just a morning drink, but coffee contains potassium, magnesium, and chlorogenic acid. Those are all ionic compounds. Then citrus juice, high in citric acid and potassium ions. Then potato water, the water left over after you boil potatoes, which is loaded with potassium, phosphate, and starch-bound minerals. Then white vinegar, which is essentially a dilute acetic acid solution, then classic salt water. And finally, something I had sitting in a jar on my counter from a batch of lacto-fermented cabbage I had made a few weeks earlier, fermented vegetable brine. That last one is where the story gets genuinely surprising. But I did not know that yet when I wrote the list. I just knew it was an ionic liquid and it deserved a spot in the test. So I set up 6 identical electrochemical cells, 1 per electrolyte. Each cell used copper and zinc electrodes of identical surface area, placed in identical glass containers with identical volumes of each liquid. I connected every cell to a digital multimeter and a precision microammeter, and I recorded output voltage and output current at 1-hour intervals for 72 hours straight. No replacing the electrolyte, no refreshing it, no touching it, just measuring and recording. I want to be upfront about something before I share the numbers, because honesty matters to me on this channel. I did not invent this methodology. I'm not claiming to have discovered something brand new. Alessandro Volta himself, the man who invented the battery in 1800, ran experiments using animal tissue, salt-soaked cardboard, and various brine solutions as electrolytes before he settled on sulfuric acid as his standard. The academic literature on organic electrolytes and galvanic cells goes back over 100 years. The Journal of Chemical Education documented the electromotive force of fruit and vegetable juice electrolytes as far back as 1938. The Indian Journal of Chemistry published comparative studies using agricultural waste streams in 2012, finding that several organic waste streams matched or even exceeded dilute sulfuric acid in short-term galvanic cell performance. This science is real. It is documented. It is peer-reviewed. What most people have never done is connect it to their own kitchen. That is the gap I'm trying to close right now, and that is exactly what this channel is about. You already know the basics of how a battery works, at least if you ever did the lemon battery experiment in school. The lemon provides acid. The acid carries ions. The ions complete the circuit between 2 different metal electrodes. That is it. That is the whole thing. The chemistry is completely identical whether the acid comes from a lemon, a jar of fermented cabbage, or an industrial tank of sulfuric acid. The electrolyte has one job, ion conductivity. The question is just how well different substances perform that job over time. And that is the key phrase, over time. Because that is where the results got genuinely surprising and where most people would have stopped the experiment before seeing what actually matters. Here's the science that makes the results make sense. Electrolyte performance in a galvanic cell depends on two main variables. First, ion concentration, meaning how many charge-carrying particles per unit volume the liquid contains. Second, ion mobility, meaning how freely those particles move through the liquid when the electric field is applied. Sulfuric acid in a lead-acid car battery has extremely high ion concentration and extremely high ion mobility, which is why it produces strong, sustained current over a long period. Natural organic electrolytes have variable ion concentrations and generally lower mobility. But variable does not mean weak. It means it depends on the specific liquid. And what I found when I ran the numbers was that one of my kitchen waste streams was performing in a way I genuinely did not see coming. Let me give you the actual data from 72 hours of continuous measurement, because this is where the story really lives. Coffee grounds, electrolyte. At the start of the test, it produced 0.71 volts and 38 microamps. After 24 hours, it dropped to 0.53 volts and 22 microamps. After 72 hours, 0.31 volts and 11 microamps. A steady, consistent decline as the organic acids broke down and the ion concentration dropped. Citrus juice electrolyte. This one started the strongest of all the organic liquids. Initial output was 0.84 volts and 61 microamps. Very impressive for a kitchen liquid. But at 24 hours, it dropped to 0.62 volts, and by 72 hours, it was down to 0.38 volts and 19 microamps. Strong start, significant decay, potato water. Weakest initial performer of the six, started at 0.49 volts and 24 microamps. The significant turbidity from starch compounds appeared to interfere with ion mobility, dragging down the performance throughout the test. Vinegar electrolyte started at 0.78 volts and 52 microamps. After 72 hours, down to 0.44 volts and 26 microamps. Decent initial performance, moderate decay. Salt water at 2% concentration, started at 0.61 volts and 33 microamps. Consistent, stable decline throughout the test period. And then the fermented vegetable brine from a 3-week lacto-fermented cabbage batch that I had made at home. At the start of the test, 0.81 volts and 58 microamps. So far, not exceptional. Citrus juice had started higher, but here's where you need to keep watching because this is the result that stopped me cold. At 24 hours, 0.77 volts and 53 microamps. Barely any change. At 48 hours, 0.73 volts and 49 microamps. Still barely any change. At 72 hours, 0.68 volts and 44 microamps. The fermented brine lost only 16% of its initial voltage over the full 72-hour period. The citrus juice lost 55%. The coffee grounds lost 56%. The vinegar lost 44%. The fermented brine did not have the highest starting output, but it had, by a very significant margin, the most sustained output across the entire test duration. And it compared directly to a 10% sulfuric acid control cell that I ran in parallel, which actually showed higher initial voltage but declined proportionally faster after the 24-hour mark due to electrode sulfation. Think about that for a second. A jar of fermented vegetable brine that most people would throw out, sitting in the back of the fridge, performed comparably to a dilute sulfuric acid solution and outperformed it in sustained output after the first day. Now let me explain why, because this is the part that makes the fermented brine result make complete scientific sense once you understand what lactofermentation actually does. Lactofermentation, the same ancient preservation process used to make sauerkraut, kimchi, pickles, and dozens of traditional foods around the world, works by encouraging lactic acid bacteria to convert sugars in the vegetable into lactic acid. That lactic acid is what preserves the food, and it is also what makes the brine acidic. But here is the part that matters for our experiment. Lactic acid is actually a stronger organic acid than citric acid, and the brine from a mature lactofermented batch is not just lactic acid. It also contains dissolved minerals from the vegetables themselves, potassium, calcium, magnesium, plus sodium chloride from the salt used in the curing process. You end up with a liquid that simultaneously contains potassium ions, calcium ions, magnesium ions, sodium ions, chloride ions, and lactate ions, all dissolved and ready to carry charge. That combined ionic content is what produced the performance I measured. It is not magic. It is just chemistry, and it is chemistry happening in a jar you might otherwise empty into your sink. I also want to address the second mistake most people make when they run this kind of test, because I almost made it myself. After the 72 hours were done, I nearly discarded the brine thinking it had been used up by the electrochemical reaction, but it had not. At the current levels these cells produce, the brine is not consumed in any meaningful way. The ions are moving, but the brine itself remains functionally intact. What degrades over time is actually the electrode, not the electrolyte. The copper and zinc gradually corrode through the galvanic reaction. The brine can be refreshed with a small addition of fresh fermented liquid and reused. This matters because it means the brine you made for food preservation has a second life as a reusable electrochemical medium at essentially zero additional cost. Now, if you want to replicate this experiment yourself, and I genuinely encourage you to try it, because running the numbers yourself and watching the voltage hold steady on that fermented brine cell is something you will not forget, here is exactly what you need. You need 6 small glass containers. Clean jam jars or drinking glasses work perfectly, and if you already have them at home, they cost you nothing. You need copper and zinc electrodes of consistent size for each cell. Copper pipe fittings of identical size run about $4 to $6 for 6 pieces. Zinc strip or galvanized sheet metal cut to matching size runs about $5 to $8. You need a digital multimeter capable of measuring in the microamp range, which you can find for about $10 to $15 for a basic unit that will do exactly what you need. And then you need your test electrolytes, which cost you absolutely nothing because they come from your kitchen waste. Coffee grounds steeped in water, fresh citrus juice, potato water from boiled potatoes, white vinegar, salt water, and fermented vegetable brine if you have it, which I would strongly recommend making before you run this test because the results are the most interesting thing in the whole experiment. Total materials cost if you buy everything from scratch, somewhere between $20 and $29, and once you have the electrodes and the multimeter, every future test costs you nothing because the electrolytes come from what you are already making and already throwing away. If you are watching this and you have never made lacto-fermented vegetables before, I want to take a moment to say that the fermentation process itself is extraordinarily simple. You shred the vegetable, you add salt, you pack it tightly into a jar, and you let the naturally occurring bacteria do all the work. 3 weeks later, you have preserved food that can last for years, and you also have a jar of functional electrolyte brine sitting right there. The same process that gives you the food gives you the brine. They come together. What this experiment means, in a bigger sense, is something I have been thinking about since I sat at that kitchen table staring at the coffee filter. We have spent 100 years treating industrial chemistry and kitchen chemistry as completely separate categories. Industrial is serious, laboratory, precise, powerful. Kitchen is casual, domestic, not really science. But the ions do not care about that distinction. The chemistry does not care. Lactic acid is lactic acid, whether it forms in a fermentation crock in your kitchen or in a laboratory flask. Potassium ions carry charge identically whether they come from a purchased reagent or the water left over from your boiled potatoes. The category we put things in does not change what they actually do. And I think there is something genuinely important in recognizing that, not just as a fun science experiment, but as a way of seeing the world. When you understand that ionic chemistry is happening in your fermentation crock, in your citrus fruit, in your morning coffee, in the brine from your pickles, you stop seeing those things as waste. You start seeing them as something that has properties, that has function, that has real measurable output. The specific quiet satisfaction of holding a multimeter lead against a copper electrode in a glass of fermented brine and watching real voltage appear on the screen is something I cannot fully describe. But it comes from the knowledge that you made that, from things you already had, from a process you already understood. This is not about replacing your power grid with fermented cabbage. That is not the point, and it was never the point. The point is understanding what these substances actually are and what they can actually do, so that you see your kitchen as a place where real chemistry is happening rather than just a place where you prepare food and throw things away. If you want to start immediately, here's the simplest version of this experiment. Take 1 glass, fill it with fermented vegetable brine if you have it, or fresh citrus juice if you do not. Take 1 strip of copper and 1 strip of zinc, or a copper coin, and a piece of galvanized metal. Drop them in without letting them touch each other. Connect your multimeter leads to the 2 electrodes. You will see voltage on the screen. Write that number down. Check it again in 12 hours. Check it again in 24. If the fermented brine number declines more slowly than you expect, you have just confirmed something that was documented in the academic literature in 1938, and that most people watching this video have genuinely never thought about. That is what this channel is about. Not just showing you interesting results, but giving you the methodology to confirm them yourself with materials you already have, so that the knowledge becomes real to you in a way that watching someone else's numbers never quite can. If this video shifted something in how you see your kitchen, I want to know about it. Drop a comment below and tell me what you are planning to test first. Share this video with someone who would never expect their leftover fermented brine to produce measurable electricity, because their reaction is going to be worth seeing. And if you are not subscribed yet, do it right now, because the next video in this series goes even deeper into practical ambient energy collection from sources most people completely ignore. The knowledge that the modern world has buried is still out there. We're just digging it up together. I will see you in the next one.